In this lesson, we will see how to deduce and calculate running time of an algorithm and analyze the time complexity of it. The actual time taken by an algorithm, or what we also call the running time of the algorithm, may depend upon a number of factors. And let us see what those factors are. So we will say that running time depends upon factors like whether your machine is a single processor machine or a multiple processor machine, and maybe also upon which generation of processor you have. Running time also depends upon what is the read or write speed onto the memory of your machine. So we'll say that read or write speed to memory or disk, because your program may have or will surely have a lot of input output operations. Running time also depends upon whether your machine is a 32-bit architecture or a 64-bit architecture. And it may also depend upon a couple of other factors or aspects relating the configuration of your machine on which you're running the program. And last but not the least, it also depends upon what input you are giving to your program or your algorithm. Now, when we talk about time complexity analysis of an algorithm, we do not bother about all these factors. All we bother about is that how our program behaves for various inputs, or how the time taken by the program grows with the input to the program. So mostly we are interested in the rate of growth of time taken with respect to the input. Now, how do we calculate an expression that gives us the rate of growth of time of an algorithm with respect to the input? To do so, we first define a model machine where we will execute our program. So let's say we define a hypothetical model machine with below characteristics. It is a single processor machine. The architecture of the machine is 32-bit. It executes the instructions in the program sequentially, and let us say it takes 1 unit of time for simple arithmetical and logical operations like addition, subtraction, multiplication, division. So 1 unit time for arithmetical and logical operations. And it also takes 1 unit of time for assignment to a variable, and also 1 unit of time to return from a function. So 1 unit for assignment and return, and let's say all other costs are negligible and we do not account for it. Now, this is a hypothetical model machine that I have defined, and you can define a model machine of your own choice where you can say that, hey, the machine takes this much amount of time for this operation. But because eventually we are interested in calculating a function that gives us the rate of growth of time with respect to input, the analysis will still be the same. Now let us pick up some very simple examples and try to deduce the functions that define the rate of growth with respect to the input. And I will clear this a little bit. Let's say we want to write a program to find the sum of two numbers a and b. So I will write a function here that will take two integers a and b and simply return a plus b. And I'm only writing a pseudocode here. Now if I want to run this particular function using the model machine, then let's say if the time taken is t, and let's say this is t sum, then 1 unit of time for the arithmetic operation addition and 1 unit of time for the return statement. So the total time would be equal to 2 units. So in this case, irrespective of the input to the program, the time taken is exactly 2 units. Or we can also say that the time taken is always constant. So this particular program is a constant time algorithm. Now let's pick up another example. Let's say we want to write a program that gives me the sum of all the elements in a list. So I would write a function sum of list that will take a one-dimensional array a as input, and let's say it also takes as argument to the function the size of the array. So the size of the array is n. So in this case the program goes like, so we start with a variable total and we initialize it to 0, and then we run a loop and keep on adding the elements of the array into this particular variable, and finally return it after we come out of the loop. And before we calculate the time taken, let's do something. Here I will label these statements with line numbers 1, 2, 3 and 4. Now line 1 has one assignment, so the cost will be 1 unit, and this particular statement will be executed exactly once. Line 2 has one comparison, which is often there in a loop, and since I've written a pseudocode here only, so let's assume that we have one comparison and one incrementation, and both have cost 1 unit each, and the total cost to execute line 2 is 2 units. And this will execute n plus 1 times, one extra time for the false condition when the program actually exits the loop. And this also has a cost of 2 units, one for the addition and one for assignment here. So this executes n times, and the last line is a simple return which executes once and has a cost of 1. So the total cost, let's say, is t sum of list is equal to 1 plus 2 into n plus 1 plus 2 into n plus 1, and this eventually evaluates to 4n plus 4. Now if this sounds a little messy to mark these absolute terms here in cost, we can also write some constants here, like the cost of executing line 1 is, say, C1, and the cost of executing line 2 can be called C2, and we can go on like this. And then also we can try to calculate the total cost. So in that case we will arrive at some expression like time taken is a function of n, Tn, which is equal to some constant, let's say c times n plus another constant c dash, where c is equal to c2 plus c3 and c dash is equal to c1 plus c2 plus c4. But these constants are not important because we are interested in the rate of growth of the time taken, and in this case clearly the time taken grows as a linear function simply because it's proportional to n. So for the first example that we had picked, we had the time taken to sum up two elements equal to some constant. Let's say this constant was k. The second example was where we wanted to have the sum of elements in list, and in this case our time taken was a linear function of n, something like c into n plus c dash, where c and c dash are some constants. If we want to print or calculate the sum of elements in a two-dimensional matrix of size n cross n, then if you try to deduce the time taken in that particular situation, the expression would be something like an square plus bn plus c, where a, b and c are some constants. So you will get some quadratic equation like this, quadratic function like this, and if we try to plot these three functions on this graph, then we get something like this. In fact, x-axis here is and should be input size, so we can call it, let's say, n. Clearly for higher values of n, the rate of growth of the quadratic function is a lot more than the rate of growth of the linear function. We often classify these functions in set, where the rate of growth of all the functions in a particular set is very similar. For example, big O of n square will define the set of all the functions of the form an square plus bn plus c. Similarly, all the functions like linear functions like Cn plus C dash would be defined by On. So On is the set of all the functions of this particular form. All the functions of the form time is equal to some constant belong to the set O1, and this is the same big O notation that we are talking about all this while. We have been talking about all this while. This classification of functions into these sets is done using the concept of asymptotic bounds, which is a very fundamental concept in time complexity analysis. Big O is actually called an asymptotic notation. So this big O that we often write is called an asymptotic notation. And we also have other asymptotic notations like theta and omega, and we'll learn about all of them in the next lesson. So thanks for watching.